Hi, you guys. Happy Thursday or whatever day it is that you are watching this video on. Um, so we finished up our stoichiometry unit, and so for our last unit, we are going to look at the application of stoichiometry in practical matters. And to do that, we need to talk about how do we do chemistry when it involves gases, and how do we do chemistry when it involves dissolving the chemical into a liquid, usually water, in order to do a chemical reaction. It's kind of challenging to get chemicals to react in the solid state, and so we often dissolve them to speed up reaction, although that's not always the case. So we'll be talking about gas and aqueous solutions, and that will be the end of our class. We may have a short quiz next week, the last week of class, but I haven't totally decided yet, so I'll keep you guys updated on that. And we will have 3 sets of lessons between now and the end of class. We're going to have an introduction to gases. We're going to talk about specific gas laws and practice using them. And then we're going to talk about solution chemistry, practice using solution chemistry, and we're done. Obviously, this quarantine has changed the pace of our class, and so we're not covering content to the breadth or depth that we normally would, and that's okay. And so I just wanted to kind of cover the bare essentials of these last 2 topics. Yeah. So anyway, I'm sorry, I'm just rambling at this point. Moving on. Introduction to gases and kinetic molecular theory. So first I want to talk about gases and their characteristics. Normally I might have you guys brainstorm some things that you think of when you think about gas. It tends to be a little tricky to conceptualize because we often can't see it, and we don't always feel it. But if you've ever, stood in front of a fan, then you can feel the air and the gas. If we were in class, I would tell you guys to fan your face really quickly so you could feel the air molecules hitting you, mostly just because it makes you look silly. So, you can do that in the comfort of your own home if you would like to experience the sensation of gas particles. But the characteristics that they have are that they can expand to fill their containers. And so if you put gas into something, it doesn't sit at the bottom like a liquid does. It expands to fill it to the full space. Gases are highly compressible. You can squish them into really small spaces. They have very low densities. The particles want to be as far apart from each other as they can be. And so they just diffuse and spread out. And so they're not very dense. And they move at really, really high speeds. Stuff in a gaseous state has a ton of kinetic energy, and they're just flying around at really, really remarkably high speeds. Kinetic molecular theory is what we use to understand the way individual gas particles behave. And even though we typically think of gas particles in large quantities, it's helpful to understand their behavior both individually and as a group. So this says that the observable properties of a gas are the consequence of the behavior of the molecules making up that gas. So we have to make some assumptions for this to really work. One assumption is that gases are ideal. So they're behaving exactly how we expect them to. Naturally, this is not completely realistic. And so when we are doing calculations and modeling the behavior of gases, we really have to differentiate and say, this is an ideal gas and it's going to interact like this. There are gases that behave less ideally, and we're not going to worry about that in this class, but that is something you could hear about in the future. The next thing we're going to assume is that the particles are in rapid motion and they're running into the container that they're in. So they're just running into the walls. So if you're sitting in a room right now, the gas particles are bouncing off the walls all around you. They're bouncing off of you, they're bouncing off each other, and they're going very fast. Gas particles have negligible size. So that means it's so small, it's really not important. Compared to the distances between them. And so even within a really tiny space, like the inside of a balloon, the size of the particles compared to how far apart they are is really, really, really tiny compared to the distance apart from them. A really important quality of ideal gases is that they have no attraction for one another. They have no polarity, they have no significant dipole forces or anything like that. They are just not attracted to each other. They're not repelled by each other. They just aren't attracted. They just don't care. And this is a really important quality of an ideal gas. We also want to keep in mind that the absolute temperature of the gas is a measure of the average kinetic energy of the gas particles. So if we're talking about increasing temperature, you're talking about increasing the kinetic energy of the gas particles. If you're increasing their kinetic energy, you're increasing their speed. And so there's this direct relationship between the temperature, the kinetic energy, and the speed. So if you take a peek at this box, this is a bunch of gas molecules represented by purple dots. The green represents the line or the walls of the container. And the arrows show the directionality of the gas molecules. So, within the system, we can see a lot is changing. The positions of the gas molecules and the direction that they're moving is constantly changing. But the number of gas molecules is staying the same. All right, so in ideal gas land, there's 4 things that are useful for us to think about. And this is on a molecular level because we can understand what's happening at an observable level by understanding what's happening to the individual molecules. So one thing we look at is the number of collisions. How often do the particles run in to the sides of the container? I'm so sorry, guys. I'm sleepy today. And then the other thing we want to know is the number of particles. And typically in chemistry, we don't talk about that in terms of like atoms or molecules, right? We actually talk about it in terms of moles because moles is such a more manageable number. We want to know about the speed, and then we want to know about the space that the gas is occupying. And when we know those things, we can understand that system. And so obviously we can't sit around and tally how many collisions there are because we can't see the particles. We can't count the particles because we can't see the particles. We can't get a little tiny miniature radar speed gun on our particles to see how fast they're going. And so we gotta find a scaled up version of those things that we can observe. So for number of collisions, we call that pressure, which is a really simple way to think of it. So if there are more collisions, there's higher pressure. Fewer collisions, less pressure. Number of particles, moles, we already talked about that. Speed, as we said earlier, is directly related to temperature, which is easily measured. And then the space occupied by the gas is defined as the volume. And there needs to be a finite sealed container in order to define volume effectively. Kinetic molecular theory aids in our understanding of what happens to gas particles as the environmental condition changes. So we can think about, if I increase the temperature, what's happening to my particles? Well, increasing the temperature doesn't change the size of their space. It doesn't change how many moles there are. That doesn't change how much stuff there is, but it is going to increase the number of collisions because they're going faster. And then you could think about, okay, well, what if I change the volume? What if I give the gas molecules a bigger container? So I didn't change the moles, I got a bigger container. It's not going to change my temperature. I didn't add or take out any energy, but the pressure is going to decrease because there's more room for all of those little particles to move around. And so they're not going to hit each other and not going to hit the walls as often. So there's a couple tenets of KMT that we like to keep in mind. The first one is that gases consist of a large number of molecules that are in continuous random motion. Second, the combined value of all the molecules of the gas is negligible, right? Too tiny to matter, relative to the total volume in which the gas is contained. So that means no matter how small your container of gas is, the molecules are way, 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 way tinier. Attractive and repulsive forces between gas molecules are negligible. They don't exist. The average kinetic energy of molecules is proportional to the absolute temperature. So if you increase temperature, kinetic energy increases. If you decrease kinetic energy, temperature decreases. There's a direct relationship there. Energy can be transferred between molecules when they collide, but the average kinetic energy of the molecules does not change over time, as long as the temperature remains constant. Okay, so that is the end of the kinetic molecular theory. You guys are going to do a POGIL. I posted a key. As you're doing that POGIL, consider some of these ideas around pressure, volume, temperature, and moles. And don't be afraid to think about it in terms of individual molecules and how they would react. All right, let me know if you guys have questions. Love you bunches, and I miss your sweet faces.